Hello and welcome to this lecture. It turns out linear transformations can be represented by matrices, and matrices can be thought of as always representing a linear transformation. Now this is a very different view of a matrix. Earlier we were viewing the matrix just as a grid of numbers for storage, for elimination, comfort like that, but now we are linking it very intimately to linear algebraic properties. Linear transformations are represented by matrices, and this will give us a lot of tools to understand linear transformations better. So let's see how that works. Okay, what we'll define here is something called matrix of a linear transformation. Okay, so to define a matrix representing a linear transformation or matrix of a linear transformation, this is what you need. You need a linear transformation to begin with, and you will need a basis. Okay, so we're going to pick the canonical basis and specify the linear transformation by what it does to the basis elements. So T of E1 is AB, let's say AE1 plus BE2. T of E2 is CD, let's say CE1 plus DE2. We've been doing this so far, I'm just repeating this. Now when you have a linear transformation and a basis and what happens to the basis vectors under the linear transformation, you can define the matrix of this linear transformation T with respect to the basis involved. We'll define it to be the 2 by 2 matrix, which is AB, CD. Notice how B goes column. Okay, so AB is the first column and CD is the second column. Basically, this is the idea. First column is the coordinates of T of E1 with respect to that basis. Second column is the coordinates of T of E2 with respect to that basis. Okay, so this is called the matrix of a linear transformation. Okay, so this is the definition at this point. Basically, you collect the column vectors from the T of E1, T of E2 and put it into the matrix structure. So this gives you that very close connection or good description of a matrix of a linear transformation using a matrix. Okay, so these numbers, instead of just thinking of them as vectors like this, we can put them together in a matrix and they end up having very nice powerful properties. Okay, so notice what happens now. If you have a u which is xy, which is xe1 plus ye2, any other point in R2, what happens to it when you do T of u? The same thing as before, right? You get x T of E1 plus y T of E2. If you plug in T of E1 and T of E2 and simplify, collect the terms, you're going to get that this point is the same as ax plus cy, comma bx plus dy, right? I hope you see that, right? So you can do the simplification. X multiplies here, y multiplies here, and then you add, you get ax plus cy, bx plus dy. Okay, that's another way to see it. Now, what does it mean in terms of the matrix? We will define matrix vector multiplication so that T of u simply becomes the same quantity. Okay, so notice what happens here. T of u is x times AB plus y times CD, and we will define this to be the product of this matrix and xy. So this is where the definition of the matrix multiplication comes from. Okay, we want this matrix whose columns are the transformations of the basis vectors to represent the linear transformation generally. If that is true, you want to define matrix vector product so that T of u becomes automatically the coordinates, right? So xc, ac, bd multiplied by xy, you get ax plus cy, bx plus dy, and that is the coordinates of T of u. Okay, so matrix vector multiplication, was earlier asking the question, where does this definition come from? It comes from the representation of linear transformations using matrices. Okay, so this is just sort of a representation that puts everything together. Now, it turns out you can also do the other way. You can also go from a matrix to a linear transformation. Supposing you start with a matrix, right? Maybe somebody gives you a 2 by 2 grid of numbers, A11, A12, A21, A22. Instead of just thinking of them as a grid of numbers, you can add a canonical basis to this space here and then think of this as defining a linear transformation. What is the linear transformation it defines? The first column is T of E1, okay, A11, A21. The first column is T of E1, A11 E1 plus A21 E2. The second column is T of E2. So A12, A22 is the second column, that's T of E2, A12 E1 plus A22 E1. So once you do this, this transformation T is represented by this matrix A over this canonical basis. Okay, so this is a way to associate any matrix you want to a linear transformation. And previously we saw any linear transformation can be associated with a matrix. So this is like a two-way connection. Every matrix represents a linear transformation. Every linear transformation can be represented by a matrix. Okay, so that concludes this little lecture. Thank you very much.